For over 100 years, we accepted a simple idea. If you want speed, you need fire. You need fuel, compression, ignition, explosion. You need noise, vibration, heat, and smoke as proof that power is being made. We romanticized it. We call it performance. We built an entire culture around controlled combustion and the sound of mechanical violence under a hood. But what if that belief was never the final chapter? What if the fastest feeling in modern driving doesn't come from fire at all? What if the most important performance breakthrough in the history of cars is not a louder engine, but the quiet disappearance of one? Imagine a piston frozen mid-blast, flames trapped in metal, smoke hanging in slow motion like time itself. Pause to ask a question. Now, shatter that image. Shatter the myth with it. In the darkness, one blue spark appears, small and silent, and then expands into a transparent electric chassis, glowing from the inside out. No pistons, no crankshaft drama, no exhaust pulses, just energy, routed with surgical precision. This is the moment most people misunderstand electric cars. They call them simple, they call them appliances, they call them glorified golf carts. But what you are looking at is a real-time energy management computer on wheels, and once you understand the physics behind it, you stop asking whether EVs are the future and start asking how combustion lasted this long. Let's start where EV performance truly lives. Under your feet, in a gas car, weight is often treated like an enemy to be reduced, hidden, or compensated for. In an EV, weight placement becomes a weapon. Thousands of lithium-ion cells are arranged in modules, engineered into a rigid battery pack mounted low in the floor, millimeters above the road surface. This does two things at once. First, it stores massive energy capacity in a tightly managed architecture. Second, it drags the center of gravity down so far that the car feels locked to the asphalt in corners and stable through aggressive transitions. You don't just drive power, you stand on top of it. The battery is not just a tank, it is structure, balance, and dynamic control built into the skeleton of the vehicle. Now ask the next question. How does that stored energy become instant motion? The battery speaks in direct current, DC. Many high-performance electric motors are controlled through alternating current waveforms, AC. Between those two worlds sits one of the most underrated pieces of modern automotive engineering, the inverter. Think of it as a lightning-fast translator and conductor in one. Raw electrical flow goes in, mathematically shaped power comes out. It switches at astonishing speeds, controlling frequency, voltage, and current with millisecond precision. Press lightly, and it meters power delicately. Press hard, and it unleashes current instantly. There is no waiting for downshifts, no turbo spool, no delay while an engine climbs to a power band. Pedal input becomes software command. Software command becomes electromagnetic action. Action becomes acceleration now, not later, and that leads us to the magnetic core of the EV advantage. A combustion engine must build revs, manage fuel-air timing, and survive internal explosions just to reach peak output. An electric motor does something radically different. It converts controlled electromagnetic fields directly into rotational force. From 0 RPM, torque is available immediately. This is why EV launches feel unreal to first-time drivers. Your body registers acceleration before your brain finishes expecting delay. It feels like being pulled by an invisible cable. No theatrical roar required. No mechanical hesitation. Just clean force. This is the magnetic secret of EV speed. Electricity does not need to warm up, negotiate gears, or ask permission from combustion physics. It simply responds. But speed is only half the story. The truly mind-bending part appears when you slow down. In a traditional car, braking throws away kinetic energy as heat. You can smell it after hard driving. You can feel it fading in repeated stops. In an EV, much of that same kinetic energy can be harvested. Lift off the accelerator, or apply the brakes, and the motor can reverse its role, behaving like a generator. Wheels push the motor pushes electrons back into the battery, and lost momentum becomes recovered range. This is regenerative braking, but the plain term hides how revolutionary it feels in practice. It is an energy refund. Every deceleration becomes a partial recharge event. Every stop can return a fraction of what acceleration spent. Gasoline cars cannot do this in the same direct, scalable way because their architecture was never designed for bidirectional energy flow at the drivetrain level. They consume and discard. EVs consume, recover, and optimize. Behind all of this is a layer most drivers never see but always benefit from: intelligent control. The battery management system monitors cell groups, temperature gradients, charge states, and safety limits continuously. Thermal systems circulate coolant to keep performance consistent in heat, cold, traffic, and fast charging scenarios. Power electronics balance demand and durability in real time. This is why an EV is best understood not as a single machine, but as a coordinated system where chemistry, software, electronics, and mechanics work as one. The drivetrain is quieter, yes, but the intelligence is louder. Every input is interpreted, every watt is accounted for, every component participates in a conversation happening thousands of times per second. Now compare energy pathways directly. Combustion takes chemical fuel, ignites it, creates heat, converts pressure to motion, then navigates complex mechanical losses before torque reaches the wheels. EVs take stored electrical energy, shape it through power electronics, and send it to motors that produce torque almost immediately. Fewer intermediates, fewer delays, fewer wasted steps. That directness is why the experience feels different even at ordinary speeds. Smooth in traffic, violent when demanded, calm and brutal at the same time. And because fewer moving assemblies are required for propulsion, the system can reduce several categories of mechanical wear that drivers have accepted for decades as normal ownership. So when you see an electric car glide through a rain-slick city at dawn, nearly silent except for tire noise and wind, understand what is really happening. Under the skin, a dense battery pack anchors the chassis. Inverters sculpt raw power into precision waveforms. Motors translate magnetism into immediate motion. Regenerative systems reclaim energy during deceleration. Thermal and battery intelligence protect longevity while sustaining performance. This is not a cosmetic evolution of the old car. This is a new logic of movement, a cleaner, tighter, more direct route from stored energy to forward motion. The future is not merely swapping one fuel source for another and calling it progress. The future is redesigning the pathway itself so less is wasted between intention and action. Less heat, less delay, less noise masquerading as power, more control, more efficiency, more intelligence per mile. No drama required, just disciplined physics executed beautifully. So here is the final question, and it's bigger than brand loyalty or habit. When your next car decision arrives, do you choose combustion history or electric precision? Do you choose the familiar rhythm of controlled explosions or the instant clarity of magnetic force guided by software? Tell me where you stand and why. I'm reading every comment, and I want the real answer: performance, cost, infrastructure, emotion, all of it. Because this transition is not just about cars, it is about how we define progress when better physics finally becomes mainstream.